In this video, we're going to look at the three-dimensional VSEPR shape for molecules with 5 things around the central atom. Examples of some of these molecules are right here. So what do I mean when I'm talking about 5 things around the central atom? Well, here is the central atom in these guys, okay? And these 5 things can either be 5 bonds to other atoms, or they can be 4 bonds and 1 lone electron pair, or 3 bonds and 2 lone electron pairs, or 2 bonds and 3 lone electron pairs. The point is these 5 things can be any combination of bonds to atoms or lone electron pairs, okay? You might notice that in all of these molecules, the central atoms are acting as exceptions to the octet rule right here, which means that these central atoms are happy to have more than 8 valence electrons. In fact, for each of these molecules, the central atom has 10 valence electrons. Anyway, we've got a whole bunch of Lewis structures of these various molecules. Let's look at what these molecules would look like in 3 dimensions in real life. Okay, we're going to start out with a molecule that has a central atom surrounded by 5 other atoms, okay? Here's what a molecule like PCl5 would look like in 3 dimensions. This is the shape that it would have. There are 2 things that I want you to notice about this kind of a molecule. The first is these 3 atoms here, okay? Check out how these 3 atoms make a line. Here's the central atom, this would be the phosphorus, and then these 2 would be chlorines. These 2 atoms that are on the top and the bottom of this molecule are called the axial atoms. So the axial atoms, as well as the central atom, make this line, 3 of them in a row, okay? Now I can twist this so that we sort of get a top-down view of the molecule. And in that case, we see that there are these 3 atoms that are connected around the middle of the molecule. We call these the equatorial atoms, and they make kind of a triangle shape. You see that here? So we have the axial atoms that make this line with the central atom, and then we have the equatorial atoms that make this triangle. And the shape of this molecule is called trigonal bipyramidal. Okay, so here is a trigonal bipyramidal molecule, and you get one of these trigonal bipyramidal molecules whenever you have a central atom that is surrounded by 5 other atoms. Okay, now let's talk about the angles of the bonds in this molecule, which is something that you often get asked about when you're doing VSEPR shapes. In this diagram here, I'm trying to show what this molecule looks like in 2 dimensions, but it's never really easy because this is kind of a complex shape, so whenever you draw it in 2 dimensions, it feels like you can't get it quite right. Anyway, I'm going to try to twist this molecule here so that it looks as much like the diagram as possible. First bonds I want to talk about are this one and this one. Let's talk about the angle between this axial and this equatorial bond. So this angle right here, the angle is there on the diagram. So this is a 90-degree angle between this axial and this equatorial bond. It's actually the same angle here. This is also a 90-degree angle. And however I twist the molecule, there's always going to be 90 degrees there, 90 degrees there. So that's the first important bond angle to keep in mind. Since this is a 90-degree angle, and this is a 90-degree angle, we can also know that the angle between these 2 axial bonds, between this bond and this bond, that the angle here is 180 degrees, which makes sense because these atoms look like they're in a straight line. They are. It's 180 degrees. Okay, now lastly, let me twist this so we can get our top-down view. And I'm trying to show this in my diagram here of the top-down view. And okay, let me just twist this. Okay, so this is what we see. Top-down the molecule, top-down in the diagram. And the angle between any of these equatorial bonds is 120 degrees, okay? So in the trigonal bipyramidal molecule, we got 90 degrees here, 180 degrees here, and then top down, got 120 degrees between all of these equatorial atoms. All right, so that's trigonal bipyramidal. I'm going to keep the trigonal bipyramidal up here because all of the other shapes for these molecules that have 5 things around the central atom, all the other molecules are related to this trigonal bipyramidal shape. Okay, so here is the next molecule. We'll take a look at SF4. And what this has is this has 4 bonds around the central atom, but then it also has this lone pair of electrons. So SF4 would look like this in 3 dimensions. Okay? Let's compare it to the trigonal bipyramidal molecule. Okay? Sort of the front view, these guys look pretty similar. We see that they have these 3 atoms in a row here, the axial, and the central, forming a line. But then take a look at this. If we look at these from the top down, you'll see that while the trigonal bipyramidal has an atom here, that atom is missing on this guy, and instead we have an unshared pair of electrons. So these unshared electron pairs this unshared electron pair is this right here. So I've got 4 atoms, and then one of these equatorial atoms that was over here on the trigonal bipyramidal, one of those has been replaced by an unshared electron pair. This shape is called a seesaw, and that's because it can kind of look like a seesaw. Can move back and forth. You can kind of see that maybe from a top view of how it looks like that. Okay, so keep in mind, seesaw looks very much like trigonal bipyramidal, except it's just missing one of its equatorial atoms. Let's talk about bond angles for the seesaw molecule. Okay, here's a diagram of the seesaw. I'm trying to sort of look at it like this. Okay, so the first thing that I want to keep in mind is that these unshared electron pairs tend to push a little harder against atoms than other atoms do. Okay, we've talked about this previously in VSEPR, which means that this unshared electron pair is going to be pushing these atoms in towards here, okay? And that's going to mean that instead of forming an exactly straight line, these 2 atoms are going to be bent in just a little bit, okay? So what that's going to mean is that this angle, the angle between these axial atoms, is going to be a little less than 180 degrees because they're getting bent in because of the repulsion from this unshared electron pair. Let me write that in here. So this is going to be a little less than 180 degrees because of the repulsion from this unshared electron pair. Okay. Now secondly, it's going to mean that since these guys are bending in, the angle between this axial and this equatorial atom is going to be a little less than 90 degrees. So there's not a great way to show it here just because of how we're drawing the diagram. But this angle here, what I mean is the angle from here to here, this angle is going to be a little bit less than 90 degrees. Now these numbers vary from molecule to molecule, which is why I'm just saying, less than 180, less than 90, because it will vary depending on the molecule you're talking about. But if you just think about how it works, it's a good way to remember that the angle is just a little bit smaller when you have these unshared electron pairs pushing. Okay. Now, let's think about the top-down view here. Once again, because we have these unshared electron pairs pushing on these atoms, it's going to be pushing these in like this, okay? So instead of exactly 120 degrees between these 2 equatorial atoms, the angle between these 2 is going to be less than 120 degrees. So these are our angles for the seesaw. They're all because this unshared electron pair pushes these equatorials inward and these axials inward like that. Okay, here's our next molecule, ClF3, and this has 3 bonds and 2 lone electron pairs. So ClF3, or other molecules that have 3 bonds and 2 electron pairs, are going to form a shape that looks like this, okay? Check out how this is related to the trigonal bipyramidal shape, okay? Let's look at this from the top down. What's going on here is that 2 of the equatorial atoms on the trigonal bipyramidal have been replaced by 2 unshared electron pairs, okay? So now I only have 1 equatorial atom left, although I still have the 2 axial atoms. So if you look at this from the side, you can see that it looks similar to the trigonal bipyramidal molecule, okay? You got this one, and this one. It's just that you're missing this and this because they've both been replaced by unshared electron pairs. This makes this kind of T-shape, so the molecule is really creatively called a T-shaped molecule. Now, bond angles for the T-shaped. We have an unshared electron pair here and an unshared electron pair here, which means that, as we said before, these are going to be pushing these atoms inward. So the angle, it's not going to make a straight line because these are going to be pushing like that because of the repulsion from those electron pairs. So that means that this angle is going to be a little bit less than 180 degrees. And it also means that this angle from the axial to the equatorial, because these are bending in, is going to be a little less than 90 degrees, all because of the repulsion coming from these unshared electron pairs. So that's what you want to keep in mind with a T-shaped molecule. Okay, and then the last molecule that we'll look at is one that has 2 bonds and 3 unshared pairs. Xenon difluoride here, 1, 2, 3 lone pairs and 2 bonds. Here is what this molecule looks like. Again, look at how it's related to the trigonal bipyramidal. It's got the 2 axial atoms, the central atom, but all 3 of the equatorial atoms have been replaced by these unshared electron pairs, 1, 2, 3, taking the place of where the equatorial atoms usually are, okay? So these 3 form a straight line, so we call this a linear molecule. And the angles here are actually very easy because all of these electron pairs are pushing evenly on the atoms on the top and on the bottom from both directions. That means that no side is being pushed more than any other. So these atoms line up in a straight line, and there's 180 degrees between these 2 axial bonds. Okay? So that is a linear molecule. Okay, so let's just review what we've learned about the shapes of these molecules that have 5 things around a central atom. When the 5 things are all 5 other atoms, you get a shape that's this, the trigonal bipyramidal, where we have these 2 axial and these 3 equatorial atoms. Okay, so if instead of having all 5 of these things be atoms, if one of them is an unshared electron pair, you get a shape that looks like this, where you only have 2 equatorial atoms. It's related to the trigonal bipyramidal, but it's missing something here. So it ends up having this seesaw shape, okay? If you have 3 atoms and 2 lone electron pairs, you're going to be missing 2 of the equatorial atoms that you would normally have on the trigonal bipyramidal shape, and you're going to end up with this T-shaped molecule, where you have 2 axial and only 1 equatorial atom left. And finally, if you've got 2 bonds and 3 lone electron pairs, you're going to be left with a linear molecule because all of your equatorial atoms are gone and you only still have the 2 axial atoms. So when you're looking at a Lewis structure and you want to figure out what the 3D shape is, just keep in mind, think about how many bonds and how many lone electron pairs it has, and then just think about which of these atoms won't be in the structure that you're making. And that's how you'll figure out what the three-dimensional shape of a molecule with 5 things around the central atom, what that's going to look like.